Anyway, the things we are now thinking about is going from natural language to general AI, quantum, and consciousness. And this actually brings us to the next to the next talk, actually. What you see here are pictures which Roger Penrose, the person who will soon appear on stage, was drawing in 1960. In 1960, when he was an undergraduate student, and he didn't like the symbols. You see on the left, you see the symbols, QABC, QFG. He didn't like them. And while an undergraduate student, he started to replace them with these pictures. And these are really the pictures we started using in the sort of story I've been telling, which gave us this new quantum formalism, which gave us quantum natural language processing and all that. And so here we have Roger Penrose. And I hope Roger will soon appear on the screen. So Sir Roger Penrose, Nobel Prize winner, 2022. Or 21, sorry. 22, yeah. In Oxford. He is in Oxford. He's supposed to be in Oxford now, in the mathematics department. Hello, Sir Roger. You hear me? Hi, Helen. Sir Roger, do you hear me?
I can hear you.
Okay, good. So this is. Hello. So we will have this fireside chat, and I will ask you some questions. I'm going to just kick off with one very quickly. What is the connection between consciousness and quantum, if there is any?
Well, my claim is that there is a connection, but it's not quite that. The connection has to do with where quantum mechanics goes wrong, if you like. Quantum mechanics consists of two parts. One is the Schrödinger equation, how a system evolves with time, and the other is the collapse of the wave function, where it doesn't evolve according to the Schrödinger equation. And there is no proper theory of the collapse of the wave function. It's a part of quantum mechanics as is used. Sorry, how much do you want me to say at the moment on this issue?
You can say as much as you want. Maybe I should say the collapse of the wave function is a part of quantum mechanics which corresponds to the fact that people know that quantum mechanics is probabilistic. So whenever you do a measurement, different things can happen. Now the collapse of the wave package means that if something happens, then the state of the system will change into something that reflects the actual outcome which happened. So that the outcome would actually then be certain. But you can just elaborate on it. What is the role of the collapse in this process of consciousness?
Well, my view, you see, there was a common view. You mentioned von Neumann earlier. A common view which was put forward mainly by Wigner, but I think von Neumann had a similar view, was that the collapse of the wave function was the result of a conscious observer looking at the system. You see, if the system just evolves by itself according to the Schrödinger equation, then there are no probabilities. It's a deterministic equation, and that's the whole story, if you like. But it's not the whole story, because the wave function collapses. Now, when does it collapse? And according to this earlier view, according to Wigner and von Neumann, it was the conscious observer looking at the system, in a sense, which meant that one alternative or another one took place rather than the superposition of both at once. Now, my view is almost the opposite of that. That is to say that the collapse of the wave function is an objective physical process which happens quite independently of conscious beings, nothing to do with conscious beings, if you like, except that, according to my own views, consciousness itself is a consequence of the collapse of the wave function. It's not that it produces the collapse of the wave function, but it's a consequence of it. So if we understood what the wave function collapse, what it was as a mathematical physics process, that would help us to understand what consciousness is. My point of view is that consciousness is something which depends upon the collapse of the wave function. The collapse of the wave function, sometimes referred to as OR, is the objective reduction of the state. Reduction of the state is the same thing as the collapse of the wave function. It's just a more polite way of saying it. And to say it's an objective process, it doesn't require conscious beings around to happen. It happens in the universe quite independently of conscious beings. But if this collapse of the wave function, which is supposed to take place in the brain, for example, as well as many other places, within the brain, it's sort of made use of and magnified, if you like, and conscious processes come about because of the sort of orchestrated, that's the terminology we use is OR. OR means orchestrated, and OR means objective reduction of the state. It also spells OR, because it means that one thing or another happens, rather than both at once. In quantum mechanics, both things at once could happen, but it sort of resolves itself to be one or the other. So that's the OR part of OR. And the OR means it has to be orchestrated. It's not just random processes. It has to be part of some organization which somehow converts these processes, which individually seem like random processes, into conscious activity.
So an obvious question then is, does this have any ramifications on the foundations of quantum mechanics and its interpretation and things like non-locality?
Well, it certainly has implications on quantum mechanics. I mean, not the OR part, if you like, it's the OR part. That is to say, the objective reduction of the state goes beyond current quantum mechanics. Current quantum mechanics is very fuzzy about when you collapse the wave function. The sort of normal view people have is that when your quantum state gets very complicated, you might have a simple system which could involve two alternatives, say A and B, and A and B could take place in superposition. So it's part of A plus a part of B could be your state. Now, the idea is that in an ordinary physical situation, this system might not remain isolated, and it gets involved with the environment. So you have lots of complicated things going on which you don't really want in a normal experiment, but your complex alternatives, A plus B, if you like, a certain amount of A plus a certain amount of B, gets involved with the environment, and it gets very complicated. And when it gets complicated, people sort of change the view they look at the system. They replace the quantum state by a thing called a density matrix. And then you can play around with this density matrix, and then it comes back again, and you can interpret its probabilities. So that's the way people normally understand the collapse of the wave functions, in terms of what's called environmental decoherence. The system gets very complicated, and then in order to deal with its complication, you collapse the wave function. But it's not really a physical process. It's just a convenience in your description. It doesn't really explain why the collapse takes place or what happens when the collapse takes place. It just gives you a formalism which enables you to proceed without worrying too much about the reality of what you're talking about.
So we have two fundamental theories of physics now. On the one hand, we have quantum, and on the other hand, we have gravity. Gravity is actually the theory of space-time, but since Einstein, and especially his theory of general relativity, mass and space-time, they're all intertwined in a single theory. So mass is all about deformations of space-time and all of that. So Sir Roger, in the sort of collapse process of the wave in consciousness, does gravity play a role there?
Well, that's the view I hold, yes. I mean, the question is, um, what is responsible for the collapse of the wave function? Now, I've written about several articles about this, but there is a conflict between the two basic principles of these two great theories. In quantum mechanics, the basic principle, if you like, is the principle of superposition. If A can happen, or if B can happen, then you have these combinations of A and B happening both at once. It's not just that both happen at once. There's a certain amount of A and a certain amount of B, and the amounts are measured in terms of complex numbers. And I won't go into the details of that, but that's the way quantum mechanics works. So it's the superposition principle, which is the basic principle of quantum mechanics. Now, the basic principle of general relativity goes back to Galileo. It's the principle of equivalence, which says that a gravitational field is equivalent to an acceleration. Or if you like, you can get rid of it by falling freely with it, as Galileo well understood. And he talked about like dropping a big rock and a little rock from the Leaning Tower of Pisa. And if there were no air resistance, he knew perfectly well that if you had a feather and a big rock, then the feather would drop more slowly. And he understood why it would drop more slowly, and that was because of air resistance. If you could eliminate all the air resistance, then the big one and the little one would drop together. There's also a nice description he gives of fireworks. You see the fireworks going up into the sky, and they explode and produce this wonderful sphere of spark. And as this sphere drops, it remains a sphere. So his point is that if you fall freely with gravity, gravity disappears. You can cancel gravity out by falling freely with it. And that's the principle of equivalence. What Einstein was able to do, you see, Galileo was saying, well, you can fall freely from the Leaning Tower and you get rid of gravity for a little while, at least until you hit the ground. But that doesn't solve the problem of if you want a theory which eliminates gravity, not just at Pisa with the Leaning Tower, but you have to have a theory which works in New York at the same time. So you have to be able to accommodate the acceleration being different in different places. And that's what Einstein's theory did. He had to develop a theory in which space-time was not altogether flat, and the curvature of space-time allowed you to have these different free falls in different places to be consistent with one another. So it's an amazing theory, and it's now confirmed to an extraordinary degree of precision, similar to quantum mechanics. Both theories are extraordinarily precise. What's not been achieved is bringing the two theories together. What people normally think is that you need to quantize gravity. That really means bringing gravity within the scope of quantum mechanics. I think the sort of general picture that people have is that quantum mechanics is about small things, gravity is about big things. And since big things are made out of small things, then if you had a good theory of small things, then you would be able to talk about big things also. So the idea is that you're bringing the theory of big things, which is general relativity, within the scope of the theory of small things, which is quantum mechanics. Now, my view is that that's not really completely correct. It's one thing you can do, which is to quantize gravity. Nobody's achieved that, I should say. Lots of attempts at that, but that has not been achieved. But there's the opposite thing of what I call gravitizing quantum mechanics. What I mean by that is making sense of the collapse of the wave function. Because the point of view which I wrote a few papers about several times about the turn of the century was that you can't have a Einsteinian view or Galilean view of gravity, in which you could eliminate gravity locally by free fall, together with the superposition principle of quantum mechanics. There is a conflict between the two, or an uncomfortableness, if you like. And to get rid of this conflict, you can say that the collapse of the wave function actually takes place in a certain length of time, which you can calculate. And that length of time depends on gravity. So suppose you have a little grain of sand, and you try to put this grain of sand into two places at once. And you can imagine putting them into two places at once. So it's part of it is in position A and another part in position B. And the state is a superposition of being in A and in B. Now, you can measure a certain uncertainty of this state. To tell you what this is, you imagine that your grain of sand, or whatever it is, well, first of all, you had two grains of sand identical on top of each other. And then you try to pull them apart into the superposition that you have of quantum mechanics. And in pulling them apart, I'm not going to consider any force except gravity. So how much gravitational force would that be to pull it apart? Well, if it's a grain of sand, it's going to be a very, very small effect. So that this will be a tiny, tiny effect. But nevertheless, that energy it costs you to pull it from one place to the other is a measure of the uncertainty in the energy of the system as a whole. And that tells you how long that system will survive being in superposition. And basically, you take the reciprocal of that energy and put it in ordinary natural units in quantum mechanics, and that tells you the lifetime of this superposition. No experiment to date has been precise enough to see whether this is correct or not. The criterion that was put forward before me by a Hungarian physicist called Diósi, and he had the same idea as I did. He didn't have the same justification for this idea as I did, and he developed his theory in a somewhat different direction from mine. The view that I hold is somewhat hard to swallow in many ways, because it requires for superposition. I don't know how much I should go into on this.
Well, I mean, I'll just have a quick question there. People are starting to do experiments today, for example, in Vienna and some other places, where they're actually starting to do experiments where they're trying to understand the interaction between quantum and gravity, for example, by trying to get a mirror in a superposition, because at that point you're sort of making light interact with matter in a quantum mechanical way. How far do you think that what you're talking about is from any experimental verification?
Well, it's a way yet. That no experiment to date has got close enough to see this. The one I'm most familiar with now is an experiment put forward by Yvette Fuentes, which you use Bose-Einstein condensates. That's a nice quantum mechanical thing, but you can put these condensates into a superposition of two locations, and then you can try and measure whether that collapse takes place in the lifetime that I'm putting forward. Now, this project would probably take 5 to 10 years to do. It's only being set up now. It's the most promising experiment of this nature which I know of. As you say, there are experiments in Vienna and other ones where you use other kinds of things to put into a superposition. They're a long way from finding this. It'll be several years yet. The Bose-Einstein condensates, you might have to wait about 10 years, I think, before the experiment can be performed. In fact, what's interesting is she's proposing a sort of preliminary type of experiment, and that is not so much to measure the actual collapse of the wave function, how the superposition of the Bose-Einstein condensate in one place and being in another goes to one or the other. But when it becomes in this superposition, there's a measure of uncomfortableness, what we call the shaking of the building. The state becomes uncomfortable. And you can perhaps measure this uncomfortableness directly, the sort of error that's involved in this superposition, which is something you can calculate. That's the calculation I was referring to earlier that I looked at theoretically, and you might be able to see if this uncomfortableness or it's an uncertainty in the energy of the system, and if that uncertainty can be measured, that would be a good indication that this collapse process is beginning to operate. That could be done in a shorter time, within a few years, I think.
Okay, that's great to hear. Okay, let's completely change the topic now. So you're talking about your theory of consciousness, and there's a lot of fuss going on about AI, especially like with things like ChatGPT. Now I should clarify, people now use AI and ChatGPT as some sort of synonyms. They're not at all synonyms. There is like a whole history of different approaches to AI, and what we now call AI today is just basically machine learning and a particular branch of machine learning. So, Sir Roger, does your theory of consciousness have any bearing on how we as humans should think about artificial intelligence? Not necessarily in the sense of today, but like in the broad sense.
Oh, absolutely true. Because the view is that artificial intelligence, as currently formed, the thing that people refer to as AI, I regard that as a misnomer. It's not intelligence at all. Intelligence, in my view, requires conscious understanding as one of its features. In fact, the argument I put forward a long time ago, a different argument from the one I've been talking about just now, has to do, well, I think it goes back to when I was a graduate student in Cambridge. I was supposed to be doing algebraic geometry, a pure mathematical topic. But I thought, 3 years is a long time. I can spend my early years looking at other things. And I went to 3 lecture courses which had nothing to do with what I was supposed to be doing. One which was a course by Hermann Bondi on general relativity, which had a big influence on me, because I did a lot of work in GR later on in life. Another was a talk by the great Paul Dirac on quantum mechanics, and I learned about quantum superpositions and things like that. And I understood about the problem that you have of the collapse of the wave function. It wasn't quite stressed as a problem at that time. The other course was a course on mathematical logic by a man called Steen. And it was a very interesting course because I had heard about Gödel's theorem before, seemed to say that there were things in mathematics you couldn't prove. And I didn't much like the idea of that. So I went to the course, and the first part of the course was describing the idea of computability, a precise notion in mathematics. Computability is what you can do with a computer, if you like. And so you can have a formal idea of what a computer is. The notion what's sometimes referred to as a Turing machine. That is a thing which a universal Turing machine can do computation. Any computation could, in principle, be done by a Turing machine. I knew what computability meant. And then he just talked about Gödel's theorem. Now, what's Gödel's theorem say? Well, it's the thing which seems to show that there are things in mathematics you can't prove. That like the idea much. But as he described it, it wasn't really like that at all. It was something which I found much more interesting. What you do is you produce a statement. The clever part, you have a set of rules which you call things that you accept as a method of proof. Suppose you settle on a set of rules which give you mathematical proofs. And these are things you could put on a computer. So computational rules which you could put on a computer and together and make a complicated chain of reasoning which you regard as a proof. And you look at these rules and you say, yes, I think I'm pretty satisfied with those rules, that if they end up with saying the statement X is true, then you believe it is actually true because you trust all the rules. Now, what Gödel does, and it's a very remarkable thing, he makes a statement which says, once you interpret it in terms of ordinary language, what it says is, I am not provable by those rules. Everything can make it do that, and that's what Gödel was able to do. It really does say, I am not provable by those rules. Okay, well, suppose it's false. It's provable by the rules. And therefore, because you trust all the rules, you've gone through them carefully, and you believe all the rules are right, and if you're provable by the rules, it must be true. And therefore, it must be true because it's provable by the rules. Therefore, it's true and not provable by the rules. And I found this absolutely amazing. How do you know it's true if it's not obtainable by those rules? What is it obtainable by? It's obtainable by the fact that you believe those rules only give you truths. You understand why the rules only give you truths. And that understanding allows you to transcend the use of the rules themselves. I found that quite amazing. It shows you that understanding, whatever the word understanding means, enables you to transcend computation. No matter what those rules are, if you can understand what the rules are, then you can see how to transcend them. That is what Gödel tells you. And from then on, I believed that whatever is involved in human understanding is not a computational. It's not something which goes on in a computer. The computer chugs away. It doesn't have understanding. It's just following rules. It doesn't know that the rules only give you truths. It doesn't know anything. It doesn't know things because it's not conscious. So the argument was that consciousness requires something beyond algorithms. Algorithms are just a general term for computational process. So an algorithm is an example, well, it means a computational process, something you could put on a computer. And this is telling me that there are things which you cannot put on a computer. I found this absolutely amazing. It also suggested to me that what is involved in conscious understanding requires going beyond computational rules. So what is going on in our heads? I'm a physicalist. I believe that what's going on in our heads is according to the laws of physics. But it's telling us, to me, that those laws of physics ultimately are not computational. There is something in those laws beyond computation. I try to think what that could be. Well, what could Newtonian mechanics? Well, you can put that on a computer pretty well. How about Einstein's general theory of relativity? You wouldn't be able to put that on a computer. In fact, I didn't know much about it at the time, but nowadays there are many problems. Black holes spiraling into each other and seeing how much comes in gravitational waves comes out, and all sorts of things like this, which shows you the power of computation in general relativity. Sure, you can put these problems onto a computer. What about quantum mechanics? Well, you can put the Schrödinger equation on a computer. What about the collapse of the wave function? This tells you where the Schrödinger equation doesn't keep going as it should. It becomes probabilistic or something like that. And I learned about this from Dirac's lectures, which I found very impressive in many ways. So we needed theory which transcended our current understanding of quantum mechanics. And that whatever is involved in our conscious understanding, consciousness enables you to do things which you can't do without consciousness. And curiously enough, you see, when you say understand, use the word understanding, what does that mean? Well, I don't really know what it means, but it certainly involves being aware of things. It doesn't seem to make sense to say if an entity understands something, if it's not even aware of it. So in your normal use of language, understanding implies consciousness, whatever that means. Now, I don't know what consciousness means, but I claim that whatever it is that it's something which involves the collapse of the wave function in an objective way. It makes use of it. The collapse of the wave function goes beyond standard quantum mechanics, and I didn't know how to achieve this, but I had this belief. And then I wrote my book, The Emperor's New Mind, which was, well, I think I'd heard some talks on the radio, which I thought, look, I can't. The idea that computability means that machines can do everything like this, I didn't really believe. So I thought I'd write a book on this topic, which was aimed at showing the collapse of the wave function could be something which is involved in consciousness. It was not the result of a computation. And I wrote the book trying to make this case, and I learned all that I could find about neurophysiology. I learned about nerve transmission and the Hodgkin-Huxley theory of nerve transmission. And then I thought, well, look, you can't preserve coherence with nerve transmission. It's going to involve the neighboring cells and all that stuff. You can't keep it isolated. You can't keep quantum coherence isolated with nerve transmission. I didn't really see how it's going to work at all. So I sort of gave up at that point. And I said, well, never mind. I rather weakly suggested something which I didn't quite believe. And that was the end of my book. I was hoping a lot of young people might be inspired by the book. Most of my correspondents were entirely old, retired people, which was a bit of a disappointment. I suppose I shouldn't worry about that. But one person who did read my book was Stuart Hameroff. And he wrote back to me to say, well, I've been looking at your book, I find it interesting, but there's something clearly you don't know about, which might really be an interesting addition to your ideas. And this was microtubules. I'd never heard of microtubules. I said, no, I've never heard of them. He came to England and we had long discussions about this. And it seemed to me that microtubules were much better candidates for preserving quantum coherence to a level where the collapse of the wave function could actually be functional. And that's the view that we heard today. It's developed very considerably. Stuart Hameroff is the person who knows about the neurophysiology. I'm very ignorant about that subject. He now has developed this subject in a way that he singles out certain particular cells. So one thing that struck me in what I did learn about neurophysiology was that you have the cerebrum, this part of the brain which people normally think of, and then right behind and underneath is the cerebellum. The cerebellum actually has more neurons in it than the cerebrum. I didn't even know that at the time I wrote my book. I knew it was a comparable number, but apparently there are more neurons in the cerebellum than the cerebrum. Also, the cerebellum is organized in a way which you might think is much more sensible. If you were going to design a computer, the cerebellum is much more like it. The left-hand side controls the left hand, the right-hand side controls the right hand, in a sensible way if you want to organize it as you would a computer. It doesn't have this crazy crossing over from one side to the other, and all sorts of things which seem to be really crazy in the cerebrum.
So there's an interesting question here, just going to the end and conceiving your entire talk. So you mentioned about your studies, that you were studying pure math, but also were studying mathematics at the same time, and also general relativity. And now we're talking about neurophysiology. How important is it, and this is sort of a general question, for scientists to be aware, oh, it's not working. What did you hear? So, how much did you hear?
If I heard you, yes.
Oh, you heard me, okay. So my question is, how important is for a scientist to be so broadly aware of different disciplines, and also let these different disciplines interplay to actually come to genuinely new insights?
Well, I think it's difficult to generalize about this, but I think it's important. In order to make progress in a particular area, you have to go deeply into that area. But it's also useful to think broad as well. So I tend to think of a funnel. Go deeply into your particular area that you're concerned with, but also have a good broad understanding of other things at the same time. So how much you can broaden out your deep understanding is a delicate matter. But I think you need both, really, to have some interest broadly in other areas, which can go as far as you can manage, and but also in your particular specialist subject, you go deeply into that. And so to try and combine both is, I think, the way I would regard as the optimal way of looking at the issue.
Okay, thank you. I think this is the end of the session now. So we thank you very much. The audience, please clap, because this is a very unique opportunity you had. You don't get a chance every day to listen to such a great mind, which is obvious from what we hear today. So thank you, Sir Roger. Thank you so much.
My pleasure.